We're ready to start the next video and the next section in our study on derivatives. In the last section, we were looking at the derivative as the slope of the tangent line to a particular point A, where we knew what the value of A was. In this section, instead, we're going to take a look at the derivative as a function. That is, finding the slope of the tangent line at any point in the domain of the function for which the derivative exists. Remember that the derivative is the limit of the difference quotient, the limit of the slopes of the secant lines. Now, in this case, we're going to be using the same three limit definition, but most of the time we'll use the x plus h definition or x plus delta x definition. That's the best one of the three in order to find the derivative as a function, instead of a single value representing the slope of the tangent line at one point. We're also going to learn to sketch the graph of the derivative. We'll also talk about the conditions under which the derivative does not exist when we're looking at the graph. So we'll be looking at graphs quite a bit today in the latter part of this section. We'll also talk about what it means to take a second derivative, the derivative of the derivative. We know, for example, that the derivative of a position function is the velocity function. It makes sense then that the derivative of velocity would be acceleration. But this means acceleration must mean taking the derivative 2 times of the position function. We call this the second derivative. Let me share my screen with you and we'll take a look at the learning objectives. Here are the learning objectives we're going to focus on in this video. We're going to define the derivative function of a given function. This means not at a specific point, but at any point in the domain of the function for which the derivative exists. Then we're going to graph a derivative function from the graph of a given function. Well, actually, we're going to do the second objective at the end of the video. We're going to talk about the connection between derivatives and continuity, and we're going to describe the conditions in which the derivative does not exist. Now, this says 3, really it's more like 4. We're also going to talk about the higher order derivatives that I talked about a moment ago. Let's go ahead and define what the derivative function is. The derivative function allows us to find a formula, an expression that will give us the value of the derivative, slope of the tangent, at any point in the domain of the function for which the derivative exists. The derivative is still the limit of the difference quotient. In this case, instead of using a plus h, we use x plus h. But otherwise, the formula is the same. We tend to use either the x plus h or x plus delta x. We don't use the other definition because we don't have a value of a. Let's recall what the other definition was. The other definition is basically giving us the derivative at a particular point, which is the limit as x approaches a of f of x minus f of a, all divided by x minus a. However, this only gives us the derivative at a. We want a formula that gives us the derivative anywhere. So we're going to focus on these two formulas that you see here. You can choose the one you think is the most helpful, the one you like the best. If you're taking physics, you may want to stick with the delta x version. If you're not, then I would probably recommend you use the x plus h version. If the derivative of a function exists, then we say at all points in the domain, we say that the function is differentiable. If it is has a derivative at a particular value, we say it is differentiable at A, provided that the derivative exists there, meaning this limit comes out to be a finite real number. Now what we want to do is we want to talk about some examples of the derivative. We're going to go ahead and rework these using the limit notation, just like we did in the last video. But this time, instead of having an A value, we will keep the variable x in the formula. The f of x part, we're just going to use the definition that was given to us. We already have f of x, it's x squared. There's no reason to find an f of a. We will still need to compute f of x plus h, which will have fewer constants in it and more variables. Let's go ahead and compute f of x plus h for this problem. This is going to give me something squared, and inside the something, I substitute x plus h, which gives me a binomial squared, which becomes x squared, double the product of the outside or inside, plus the last term squared. Now that I have the pieces for the difference quotient, I can take the limit of the difference quotient by putting them all together. A formula for the derivative is given by f prime of x, where the prime represents the derivative notation. We'll see other ways of writing the derivative later in this video. This becomes the limit as h or delta x goes to 0 of our x squared plus 2hx plus h squared minus x squared, all divided by h. The first thing we always try is to substitute the value that the limit is approaching, which is 0. However, x squared minus x squared will cancel, and the h's in the numerator will cause 0 over 0, which is that indeterminate form. I know I've got to clean it up a little bit and maybe apply some algebra in order to be able to find the limit. When I clean it up a little bit, I get the sum of these two, but again, I'm still going to get 0 over 0. So the next thing I'm going to do is I'm going to factor out an h. Even if I could factor out more, the only thing I'm interested in canceling is this h in the denominator that's causing the problem. So I factor out that variable, and that leaves behind 2x plus h in parentheses. The single h factors cancel, and I'm left with the limit of 2x plus h. Then I can substitute 0 in place of h, which gives me 2x. What does this mean? This means that the derivative of the function f of x is equal to 2x. In other words, I've got a formula to find the derivative at any point on x squared by computing it in this function. So for example, what if I want to know the slope of the tangent line when x equals 3? Substitute 3 and I get 6. We know the tangent line at 3 will have a slope of, yes, the tangent line at 3 will have a slope of 6. Let's now look at another example. Go ahead and pause the video, work this one out, then turn the video back on and we'll compare. Let's compare our results. In this particular problem, our function is the square root of 2x. We already know what f of x is going to be. There's nothing for us to compute there. Instead, we're going to start with f of x plus h and replace the x in our definition of the function with x plus h. I went ahead and multiplied this out to get 2x plus 2h. Then I use the limit of the difference quotient to try to find the value of the derivative function. When I do that, remember, we try to substitute at each step every time we change something. In this case, if h is 0, I get root 2x minus itself, which is 0, divided by 0. It's indeterminate for a limit. It does not exist for a function, but for a limit, it just means I don't know what happens. So I have to do something. Because of the square roots, I decided to use the conjugate. So I multiplied by the conjugate of the numerator divided by itself. This is just the number of 1 in disguise. When we multiply out the numerator, it will follow that conjugate pattern that gives us the difference of 2 squares. Outside and inside products are identical, but with opposite signs. So they cancel out. That gives us the first term squared minus the second term squared. Again, I've done something, so I try to substitute the limit value, h is 0. But again, it leads to the indeterminate 0 over 0 form. Then I go ahead and notice that I can cancel the 2x that's in the numerator. This still gives me an h factor by itself in numerator and denominator, still creating that indeterminate form. Finally, I go ahead and cancel that single h factor. At that point, when I substitute, I no longer have the 0 over 0 form. Instead, when I replace h with 0, I get the square root of 2x plus the square root of 2x, which is 2 square roots of 2x. The 2 factor by itself outside the radical cancels with the 2 in the numerator, giving me 1 divided by the square root of 2x. Let's move on to example 3. Example 3 is more complicated in that we have 2 terms and we have a fraction. When you're dealing with something like this, it usually is best, because you're going to have to use the difference quotient, which is itself a fraction, to go ahead and combine your terms into one single fraction. So the first thing I recommend doing is rewriting the function f of x by multiplying the first term by x over x. X divided by x is, of course, the number 1, and this will lead us to be able to write x squared divided by x plus 1 over x, which equals x squared plus 1 over x. Now that we have it in one combined fraction, go ahead and try to find the value of the derivative function by taking the limit of the difference quotient. Pause the video now, and then we'll check our results. So let's now compare. This is a much longer problem, doing it the way we're doing it. Again, I got a common fraction, and when I substitute this into the difference quotient, I'm going to have a complex fraction. First, I found f of x plus h, which means that I take the x plus h and square it according to my new function, plus 1 divided by x plus h. In other words, the first term in the numerator is itself a fraction, and I write it here. Then I subtract the definition of the function, which you see as the second term in the numerator. Then it's all divided by h. If you try to substitute h for 0 or 0 for h, you're going to get the indeterminate form 0 over 0. I don't like the complex fraction, so instead what I do is I look for the many denominators. To do that, I need to rewrite the h in the denominator as h divided by 1. The primary division bar is this one here. Then my miniature denominators are the group factor x plus h in parentheses, the single term factor x, and the factor 1. I build the lowest common denominator from these many denominators, and then I'm going to multiply the difference quotient by a form of 1 consisting of that many denominator, x times the group factor x plus h divided by itself. I like to write it in the same complex form that my difference quotient is written in. Then I distribute the numerator over each term in the numerator and the denominator to the denominator. Like normal, I'm going to leave the denominator factored since I'm hoping something will cancel. There's only one term in the denominator. The two terms in the numerator tell me I probably have to do algebra to simplify it. When I distribute over the first term, the group factor cancels. And that leaves x to be multiplied by the numerator of the first term in the numerator, which gives me this. When I distribute over the second term, it's the single x that cancels, and that leaves me with the group x squared plus 1 times the group x plus h. I went ahead and multiplied out the two binomials in gray here, so I would be sure I wouldn't mess up my signs. It takes just a couple seconds longer, but if you mess it up, it can create a 10-minute to 30-minute problem. Take the time to multiply it out and then distribute the negative. When I simplify the numerator, I end up with the expression that you see here. I went ahead, since we've done this so many times, and I started canceling the things that were alike. Notice, however, that these two terms are not alike. I have h to the first x squared and x h squared. This term, however, does match this term. They're both hx squared, so I combine them to get hx squared. Then I have this xh squared term, and finally minus h. It's a good idea to mark through these with a different color to be sure you have them all. Again, it's divided by the combination of the factors you see in the denominator. If I try to substitute 0 for h, I still get the indeterminate form because of this single factor of h in the denominator. I factor out that single factor from the numerator, and it cancels in the denominator. Now, when I substitute 0 in place of that variable, I'm not going to get the indeterminate form. Instead, I get x squared minus 1 divided by x squared. Because the denominator is a single term representation, we can divide each term in the numerator by the denominator, and it could be written 1 minus 1 over x squared. I don't have a preference to how you write it, so you can leave it in either form. Now, this does bring up an interesting point. Could I have done this problem in an easier way using the limit laws? The answer is yes. The result here is showing us how that might be accomplished. Let's go back and look at the beginning. When I'm up here, it has the function f of x equal to x plus 1 divided by x. I know that by definition, the derivative is in fact a limit. And since the derivative is in fact a limit, I can use the limit laws. And the limit laws tell me that the limit of a sum is the sum of the limits. I could instead have found the derivative of the first term x and the derivative of the second term 1 over x separately. And when I have their derivatives, combine them together by adding. Believe it or not, even though it's doubling the work of the derivative and the difference quotient, it would result in much simpler calculations. Let's now talk about equivalent notations. When we're talking about equivalent notations, we have a lot of ways to write the derivative. When we look at the derivative, we've been writing it with what's called the prime notation. We can just write the function name with the prime and not indicate the independent variable, or we can write it with the independent variable next to it. We also have another notation, which is Leibniz's notation, this d over dx. In fact, the d over dx is one symbol. It is not a fraction with a numerator and denominator. Now, that said, it behaves like a fraction, and so we treat it like a fraction, but it is not. It is one symbol, d by dx, which represents the derivative operation, like a multiplication operation. I can follow that notation with f of x, indicating the independent variable, or I can leave off the of x and just write df dx. And that's how we would say it, df dx. But f, of course, is representing the y variable, so I could write dy dx. I can also write the y as a function of x off to the side or in the numerator. But if f of x represents y, then I could also write y prime or y prime of x. We use all of the notations I've talked about so far quite frequently in calculus. The last two, the d with the x written below and to the right in a subscript notation, and the d with the x below and to the right of f of x. These two notations we pretty much only use in calculus 3 when we're talking about the directional derivative and some of the higher order derivatives with respect to one variable only. You will see those two in Cal 3, but probably not until then. Now, remember that this is one symbol and it represents to take the derivative of whatever function follows it. It means the same thing as the prime notation. If I want to know the derivative at a particular value, say 5, I could indicate that with f prime of 5 by putting the 5 in parentheses. It doesn't mean multiply the derivative by 5. It means find the derivative at x equals 5. And this notation here with the long vertical bar on the right of the derivative notation with a small x equal a at the bottom is another way of writing this f prime of a notation. It means go find the derivative of the function named x, f, at the value x equals a. Now, these notations are in fact Leibniz's notations. They are the most commonly used forms followed by the prime notation. This d by dx or dy dx are very commonly used in calculus. When we pronounce it, allow a slight pause between the dy and the dx. It's dy dx, not dy dx, all right? Although a lot of students do say dy dx. You can also say d by dx. It represents the derivative with respect to the x variable. Now, let's bring this back to our talk about the slopes of secant lines so that we can relate this to the slope of the secant line. When we look at the graph, remember that the derivative is the limit as the secant lines get closer and closer to the point that we want to evaluate the slope of the tangent line at. Because we can write the slope of the secant line as the change in y over the change in x using the Greek letter delta, we can write this as delta y over delta x inside the limit as delta x goes to 0. In other words, on our graph, we are fixing it and we're taking secant lines that get closer and closer and closer. Our change in x is getting smaller and smaller and smaller. The derivative of the function y with respect to x is the limit of the slope of the secant line. Later in this chapter, we're going to talk more specifically about the relationship between the dy and the delta y, and the dx and the delta x. We call the dy and the dx differentials. We'll see more later this semester exactly what the differential is to help you understand better how all this relates. Now we would turn our attention to derivatives and continuity. What is the relationship between having a derivative and being continuous? Remember, if a function is differentiable at a point, then a unique tangent line exists at that point, and the slope is a single finite real value. That limit of the difference quotient exists. If a function is differentiable at a point, say at x equals 5, then it turns out it has to be continuous there. Now remember what it means to be continuous. It means that f at that value exists, f of 5 exists. The limit as x approaches 5 of f of x exists. The two-sided limit is pointing to the same number. And the limit as x approaches 5 of the function equals the function value. Function value is here, and the two-sided limit is pointing to that value. That's what it means to be continuous. However, the converse, reversing the order, is not necessarily true. We do have the statement, if differentiable, then continuous. Differentiable. It does not work the other way around. Continue, I lost a U, us. You cannot say if it's continuous, it has to have a derivative. That's not true. Let's think about the absolute value function, which is definitely continuous over the real number line. It's continuous because I can draw the graph without lifting my pencil. At every point, the function value exists, the two-sided limit exists, and they point to the same place. It is continuous. However, at the origin, where I have that sharp corner, the derivative does not exist. Now, why does the derivative not exist at the origin for an absolute value? The derivative is the slope of the difference quotient. In that case, if I'm thinking about the ordered pair 0, 0, I can use the f of x minus f of a formula to find the derivative. F of x minus f of 0 over x minus 0. The definition of f of x is the absolute value of x. And I end up with the limit as x approaches 0 of the absolute value of x divided by x. Now remember that the absolute value is a piecewise defined function. If the value is already not negative, then just leave it alone. If it's negative, you have to multiply it by another negative to force it to be non-negative. This will make it be positive. Now let's take those representations for absolute value and put them into our limit. Again, for the limit to exist, the limit from the left and the limit from the right have to point to the same value. When we take the limit as x approaches 0 from the left side, and again up here in the graph, you're coming down from numbers to the left of the origin, you can tell that you would have negative x values, so you have to replace the absolute value with negative x, which leads to -1. This makes sense. If you're looking at this part of the graph, the slope here is -1. And on a slanted line, the slope of the line is the tangent. It is the slope of the tangent line. When we take a look as we approach 0 from the right, my dog is at my feet, so I'm kind of gingerly stepping around. When we're coming from the right, however, again, we have a line. The slope of this line is positive 1. Because the x values are approaching 0 from the right, where they're all positive, we would replace the absolute value with x, which means the limit from the right is a positive 1. Because the two-sided limit does not agree, it does not exist, which means it's not differentiable at that corner. In general, functions are not differentiable at corners, sharp points. Let's now go ahead and prove this theorem that if it's differentiable, it must be continuous. We're going to let the function f of x be defined and a be in its domain. We're going to say if f is differentiable at a, then it has to be continuous there. We're going to assume in the proof that the if part is true. We're going to assume that it is differentiable at a. Therefore, by definition of the derivative, f prime at a must be the limit as x approaches a of the difference quotient. And I chose, because I was finding it at a point, to use the f of x minus f of a divided by x minus a form. Now, what does this imply? We know, because we know that is a finite real number, that this must mean that f of a does exist. If f of a did not exist, that would not end up being a finite real number. We can also rewrite this using the sum and difference laws to show that the limit as x approaches a of f of x must exist. In other words, I can take the difference quotient and I can use the limit law that the limit of a quotient is the quotient of the limits, and the limit of a difference is the difference of the limits. Now remember, we know the value of a, so f of a is a constant, and the limit of a constant is the constant. So we end up with this form on the right. But this is still the derivative, which we know exists and is a finite real number. That tells me that the limit, the two-sided limit as x approaches a of the function exists. There are 3 conditions to prove continuity, and we have 2. F of a must exist, and the two-sided limit must exist. We have 1 left. We have to prove that the two-sided limit and the function value are at the same point. How do we do this? Well, we apply a sort of a trick. The trick is called adding 0. We're going to start with the limit of f of x as x approaches a. We're going to add 0 in the form of subtracting f of a and adding it, which of course gives us 0. Meaning we haven't really done anything. I write this in the parentheses right here. Since this represents 0, I'm allowed to add it anywhere, anytime I feel like it. And then I'm going to group the terms. It's a little bit hard to see on here, so I'm going to make these larger. I'm grouping the f of x minus f of a together and leaving the plus f of a outside. Then I multiply by a form of 1, x minus a over x minus a. Can you see where I'm going? I'm trying to build the definition of the derivative. I need it to be applied to the f of x minus f of a part, so I multiply the numerator by x minus a and the denominator by x minus a. Then I use the product and sum law for limits in order to split apart this product and to split apart the sum, writing the limit as x approaches a of f of a. Now, I know that the limit as x approaches a of f of a is just f of a because it's a constant. I know what a is. On this part right here, I know what this first limit is. It's the derivative at a. I replace that part with f prime of a. However, the limit of x minus a as x approaches a goes to 0. When I substitute a for x, I get a minus a, which gives me 0. 0 times a finite real number is 0. And this tells me that the limit of f of x as x approaches a, the two-sided limit, must be pointing directly to the function value. And this proves that it is, in fact, continuous. So we end our proof with a QED after restating the 3 conditions of continuity. Now, the reverse is not true. We're going to take a look at some continuous functions that fail to be differentiable for various reasons. We've already talked about the absolute value, which has a problem at the corner. All corners, sharp points, are not going to be differentiable. Now we want to look at the graph of y equal x to the 2/3. It comes in kind of like a, well, like a child draws a bird. It's kind of coming in like this. We call that a cusp. You can also call it a sharp point. It's called a cusp. In general, functions are not differentiable at cusps. When we take a look at this, what happens is that we have one slope coming from the right and a different slope coming from the left. Let's go ahead and take a look at the difference quotient as we approach from both directions. I want to find the derivative as I approach 0 from the right, which means I'm coming from this direction and coming down this part of the graph. I can tell that the slopes are all positive as I come from the right. When I do that, I use the definition at the origin again to represent x to the 2/3 power minus 0 over x minus 0. When I simplify, I get 1 over x to the 1/3, which is basically 1 over the cube root of x. Right? Now, when I'm looking at this one, I'm again approaching 0 from numbers that are on, wait, I'm looking at the wrong one. Positive, here we go, from the right. I'm looking at numbers that are approaching 0 from the right. Now, the graph of the cube root looks like the following graph. This is the graph of the cube root. When we're approaching 0 from the right, notice that all the values are positive. That means in my limit up here that I am approaching 0, but with positive numbers in this second limit. I get a constant over something approaching 0, which we know goes to infinity or negative infinity. But because the 1 is positive and we're approaching from the right, it must go to positive infinity. When I look at the graph approaching from the left, all the x values are negative. And I can see as I trace down that curve that all the slopes of the tangent line are negatively sloped. When I substitute this in, I end up with the same limit at the end, but approaching 0 from below. Again, if we look at the graph of the cube root, you'll see that as we approach 0, it hits the value of 0 here at 0. But until then, from the left, all the values are negative. That means that it must be approaching negative infinity. Now, we have a problem. Actually, we have two. The limit from the left and the limit from the right do not agree. One goes up, one goes down. That's one problem. That means the two-sided limit does not exist. But the second reason it does not exist is because infinity and negative infinity are not finite real numbers. If you end up with infinity for the value of the derivative does not exist there. Now let's take a look at another type of problem where we have vertical tangent lines. We're going to focus this time on the graph of the cube root of x. This graph is smooth and it's continuous. You can draw it without picking up your pencil, but it does have a discontinuity or well, how would you say it? It's not differentiable at 0. Right at 0, can you see what's happening to the slope of the tangent line? Let's draw some mini tangent lines as we come down. Notice that they're all positively sloped. But what's happening is that coming from the right, it looks like the slope is going up a lot, which means it's approaching positive infinity. That's not a finite real number. From the left side, if we look at the slopes of the tangent lines coming in, they're also positively sloped and also getting larger and larger in the slope value, which means they're also going to infinity. Both sides agree, let's go to infinity. Infinity is not a finite real number. It is not differentiable at the origin because it has a vertical tangent line at that point. And what's the slope of a vertical line? That's right, it's undefined. Undefined is not a finite real number. There's no derivative there. There's another type that occurs less often. We want to take a look at this piecewise defined function. If I only had x sine of 1 over x, it would not have a point at the origin because of the 1 over x. That means it would not be continuous because there would at least be a hole of some kind or a break in the graph at the origin. If it's not continuous, it cannot be differentiable because being differentiable means you're continuous. However, if I define it with a piecewise defined function and I force the value at the origin to be 0, then I know that I have a function that's defined for all values of x. It does exist at 0. The function value at 0 is 0. Let's establish that it is in fact continuous. It's not continuous, it can't be differentiable. Does the two-sided limit exist? Let's take a look at the graph and we can predict from the graph what's happening. All right, when you look at this, can you see that we are using the squeeze theorem? We have x times sine of 1 over x and x times sine of 1 over x. I'm going to make sure that is the function. Yes. X times sine of 1 over x has to be sandwiched between x times 1 and x times negative 1. Because sine goes between 1 and negative 1. That means that it has to be between the graphs of negative x and x. And you can see the graphs of x and negative x right here. You finish drawing. Relatively straight. We can use the squeeze theorem to say that the limit as we approach 0 of negative x is 0, and the limit as we approach 0 of x is also 0. And since this function is squeezed between the two, it has to have the same limit at 0. In other words, it's pointing at 0. Now to finish continuity, we need to establish that that's the function value there. But by our piecewise defined function, that is the value there. When x is 0, the y value is 0. So it's definitely continuous. The question is, does it have a derivative? It is smooth. It is curving. There's no corner and there's no cusp. Because it's sine, there's also no vertical tangent line. But is it differentiable at the origin? The answer is actually no. What's happening as it gets closer and closer to the origin is it's oscillating faster and faster and faster. There's no one unique tangent line at the origin. The oscillation barely to the left and barely to the right of the origin are happening so rapidly that the slopes of the secant lines are changing very rapidly. Small amounts apart, but still not the same. There's no limit that exists there. And that means it's not differentiable due to oscillation. If you can't draw one unique tangent line at the point, then the derivative does not exist. Let's take a look now at example 4. In example 4, we want to find values for m and b that make this function both continuous and differentiable at 3. We're going to start with continuity because if it's not continuous, it is not differentiable. All right? Now, it can be continuous and not be differentiable, but if it's not continuous, it's not differentiable. Let's start with our 3 conditions for continuity. F of A, well, maybe I should use this space over here. F of A exists. Let's establish that that works. In this case, my A value is 3. F of 3, according to the second rule, where x is greater than or equal to 3, is the value of x squared. So F of 3 is 3 squared, or 9. That checks out. The second condition that we have to meet is that the limit as x approaches that value of A, or 3, has to exist. Now, the limit of the function can be written with the function from each side of that connecting point. In other words, I need to show the limit from the right and the limit from the left both exist and point to the same value. On the left side of 3, I'm using the rule mx plus b. So as x approaches 3 from numbers that are smaller than 3, I use the rule mx plus b. When I substitute that value in, I get 3m plus b. I know that the limit from the left would be 3m plus b. What about the limit from the right? From the right, I use the second piece, x squared, and when I substitute, I get that it's 9. In order to have a two-sided limit, this means, therefore, and I'm using that special notation, that 3m plus b must equal 9. Now, that's only one equation, so it does not give me enough information to solve for m and b. I need at least 2 variables or 2 equations for each of the 2 variables. What about the third part? The third part says that the limit value has to be equal to the function value, which we've pretty much already written that one down. We'll check this one again at the end. The limit as x approaches 3 of the function, in our case, has to equal 9. We can't check that one yet, just like we can't quite check the second one yet. Now we need to use the differentiability at 3. To be differentiable at 3 means that the limit of the difference quotient exists. Let's go ahead and write down that one at this time. I'll change colors so it contrasts a little bit. To be differentiable at 3, means that the limit as x approaches 3 of the function f of x minus f of 3 divided by x minus 3 exists. Right? I've got to have that existing. However, I've got two sides, a left and a right, using different representations for the function value. I'm going to have to split this into the derivative from the left and the derivative from the right. So the limit of the difference quotient approaching 3 from the left, my function value is mx plus b. So I have mx plus b minus f of 3, which we know is 9, divided by x minus 3. I know this one has to exist. Now, what about the limit from the right? This is from the left. Now let's do the limit from the right. The limit from the right establishes the rule x squared, and I get x squared minus 9 divided by x minus 3 must exist. And in fact, for the derivative to exist, these guys better be equal to each other. The two-sided limit has to exist for the derivative to exist. Now, there's not a lot that I can do with the derivative from the left because I don't know anything about m or b. In the second one, however, there is something I can do. I know that x squared minus 9 factors as x minus 3, x plus 3. So let's go ahead and factor that one now. This one becomes the limit as x approaches 3 from the right of x minus 3 times x plus 3 divided by x minus 3. It does give us that 0 over 0 indeterminate form until we cancel the common factor. Then when I substitute, I get that the limit here must be equal to 3 plus 3, which is equal to 6. Oh, well, if that has to equal 6, then this one also has to equal 6. That means that the slope of the tangent line from the right is 6, and the slope of the tangent line from the left has to be 6. And what is that going to tell me? How can I complete this problem? To complete it, we need to apply a sort of I hesitate to say trick, but a technique. Instead of assuming that this is 9, let's use the rule from this side, the left, to rewrite f of 3. What would f of 3 be from the left side of 3? Of course, our rule is mx plus b, which means that our rule is going to be m times 3 plus b, which gives me 3m plus b. I need these two sides to be equal to each other, which means that I can now replace that in the limit from the left to get mx plus b minus the quantity 3m plus b, all divided by x minus 3. Now, if I distribute the negative, I get minus 3m minus b. So the b's will cancel. And I end up with the following representation. The limit as x approaches 3 from the left of mx minus 3m divided by x minus 3. Yes, you can see it. We need to factor out the common m. This then leads to the limit as x approaches 3 from the left of m times x minus 3 divided by itself, which cancels. And that gives me the limit as x approaches 3 from the left of m, which is just m. But the limit from the left has to be the limit from the right, so it has to be 6. Now I can come back to the equation that we found earlier from our continuity, 3m plus b equals 9. If I know m must be 6, and m equals 6, then I can substitute and I get 3 times 6 plus b equals 9, which gives me that b is equal to 9 minus 18, or negative 9. I know the value of b must be negative 9, and the value of m must be 6. Let's now look at some higher order derivatives. The derivative of a function is itself a function, so we can find the derivative of a derivative. For example, if we think about the position function, where you are at a point in time, let's say feet, or better yet, let's go with miles, then we know that the rate of change of position, and rate of change is the derivative, becomes the velocity, miles per hour. The way the miles, the position, is changing with respect to time. However, it makes sense that the rate of change of velocity would then be the acceleration, which would be the rate of change of miles per hour with respect to time again, or miles per hour squared. But that means that the acceleration is the second derivative of position. It turns out that acceleration also has a derivative, which we call jerk. And I'm sure you're familiar with this. If you've ever been in a car and someone floors the accelerator, you get jerked backwards. Or if they press on the brake really hard, you get jerked forward. That jerk is the derivative of the acceleration. In this case, the jerk then is the second derivative of velocity and the third derivative of position. We're going to be taking multiple derivatives, and in general, we call all of them higher order derivatives. When we're looking at this, let's express the notation, and we'll start with the second derivative. For the second derivative, we often use the prime notation, and instead of 1 prime, because it's a second derivative, we use 2. You could write it without indicating the independent variable x, or you can include it. You could also write y double prime of x, and that is how we say it, double prime, or y double prime. Switching to Leibniz's genius notation, we have a 2 between the d and the y in the numerator. It's not a fraction, it's a single symbol, but we'll call it that, in the power position. This is read the second derivative of y with respect to x both times. When you get to calculus 3, you're going to have more than one independent variable. You have to know which one you're taking the derivative with respect to. Notice that the 2 in the power position in the top part is between the d and y, whereas in the denominator part, it follows the variable x. We can replace the y with f or with f of x. For the third derivative, we continue this pattern by increasing the number of primes to 3, and we say triple prime. This would be f triple prime of x, indicating the independent variable is x, f triple prime, y triple prime of x, y triple prime. And notice for the third derivative, the 3 goes in the power position between d and y and after the x in the lower part. What about 4? You probably guessed we use 4 tick marks. We don't. After 3, we give up on the primes because there's just too many tick marks. Instead, we use a notation which does cause problems for lots of students. We put the number of the derivative in parentheses in the power position above the name and to the right of the function name. This reads the 4th derivative of f with respect to x, the 4th derivative of f, the 4th derivative of y with respect to x, and so on. Notice that when we switch to Leibniz's notation, we do not have to put the 4 in parentheses. The 4 in parentheses is not optional if you're not using Leibniz's notation. It's required. The 5th derivative, 6th derivative, and so on is given in the same way. Here I've represented any arbitrary higher order derivative using n as the derivative. Notice when we don't use Leibniz's notation, it must be in parentheses, but in Leibniz's notation, it does not. Now, I want to show you an example of what it means if it's not in parentheses. If you have a function, x to the 4th minus x cubed plus 2, something like that, and you write f and a 4 in parentheses in the power position of x, you mean the 4th derivative. Apply the derivative operation 4 times to that function. However, if you write f with a 4 in the power position not in parentheses, it does represent the 4th power, meaning multiply that function by itself 4 times. The parentheses around higher order derivatives, when not using Leibniz's notation, are not optional. Now, we can also represent these derivatives by the derivative of the derivative. The second derivative of y with respect to x both times means we took the derivative once, dy dx, and then we apply the derivative operation with respect to x again. The third derivative then must be the derivative of dy dx, and so on. Let's now look at some examples of higher order derivatives. For example 5, we want to find the second derivative of the function f of x equals x squared. That means that to find the second derivative, we place the first derivative into the difference quotient, and we take the limit of the difference quotient again. Now, we've already found the derivative of x squared in example 1, so we don't need to repeat the work. Let's go to example 1 and find our result. We found that the first derivative of x squared is the function 2x. Let's now go back to example 5 and use that information. The first derivative, or f prime of x, is equal to 2x. Now I need to compute what f prime of x plus h is. Remember that I'll be using, this definition here to replace the f prime of x. And somehow that got a mark in it. There we go. Let's now write f prime of x plus h. That means we replace the variable with the expression in parentheses, giving us 2x plus 2h. Now we can find the second derivative, f double prime of x, by finding the limit of the difference quotient. Pause the video, work it out, turn it back on and we'll compare. Let's see what we have. Using the first derivative as our function inside the difference quotient eventually leads to the value of 2. Notice this means that the function is x squared, the first derivative is 2x, and the second derivative is 2. There is a pattern there, and we're going to learn all about these patterns in the next section. Your life is going to get much better after we complete this particular section. Then you will not have to use the limit definition of the derivative, but you need to be able to do it on the exam since most professors ask for it. Let's look at example 6. The position of a particle along the coordinate axis at time t in seconds is given by s of t equals t cubed in meters. Find the function that describes its acceleration at time t, a of t. Acceleration is the second derivative of position, so I need to take the derivative twice. This is one we've not worked out before, so pause the video, find the first derivative, then find the second derivative, then turn the video back on to check your answer. Let's go ahead and compare our results. To find the first derivative, I need to find the position function at t plus h, which means cubing it. To do that, I'm going to multiply 2 of the binomials together first, then distribute the third binomial. This gives me the expression you see here. Then to find the first derivative, I place this in the limit of the difference quotient. Notice that the t cubes cancel. It's still going to give me 0 over 0 because I have an h single factor in the top and the bottom. The next thing to do is to factor out this single factor of h and cancel it. Now when I substitute 0 for h, I get 3t squared as the first derivative of position. This is the velocity function, v of t. To find the acceleration, I need to apply the derivative to the velocity function, or the first derivative of position. So I apply the limit, again, of the difference quotient using the first derivative as the function. Again, I need to substitute t plus h in place of x to find the first term in the numerator. This time, I'm using 3t squared as the function. When I multiply it out and put it into the difference quotient, I get cancellation of one term. Still gives me 0 over 0 because there is a hidden single h factor in the numerator. It will cancel with the denominator when I factor it out. And then when I substitute 0 in place of h, I get 16. This means that our position function is t cubed. Our velocity function, or first derivative of position, is 3t squared. And our acceleration, which is the first derivative of velocity, and the second derivative of position, is 16. You may be wondering what's the jerk, which is the derivative of acceleration. It would be 6. Now let's take a look at the last part of this particular section, which is an applied problem. In this applied problem, we have a graph which is modeling the number of people who have come down with the flu T weeks after the initial outbreak in a town with a population of 50,000. We want to describe what the derivative represents and how it's behaving as time progresses. When we look at this, we can tell the initial outbreak is when t equals 0. A small number of people came down with the flu. If we think of the derivative as the slope of the tangent line, what that's telling us about is the change in the number of people with the flu with respect to time. In other words, the derivative represents how fast this flu is spreading. So as we look at the graph, notice it starts out with not a terribly steep, but still positively sloped tangent line. And then it gets steeper and steeper and steeper until it reaches a point where it stops getting steeper and starts flattening out. We call this point, which is probably about here, the inflection point. We're going to use inflection points to help us draw the graph of the derivative on the graph of the function. An inflection point is where the rate of change of the derivative has reached a maximum or a minimum. In our case, it's getting steeper and steeper, and then it starts to get flatter and flatter, which means the inflection point corresponds to a maximum in the graph of the derivative. As we come back across, again, it's becoming less and less steep. On this part right here, it goes nearly, but not quite, horizontal. This is called a logistical graph. What does it mean? The number of people who came down with the flu initially is here, then it spreads faster and faster and faster and faster until right here at the inflection point. Depending on where you think the inflection point is, and it's a little difficult to tell, that is when the flu was spreading the fastest at that number of weeks. Now, when we look at this part, it's still spreading. The slope is positive, but slower and slower. And when it reaches about 5 weeks, it really drastically stops spreading as much. In other words, everybody has already had the flu. And it continues to spread, but very minimally. Now, how can you locate this inflection point? I'm going to take my pictures off so we can see the curve a little more clearly again. Can you see that this part of the graph down here is cupped up, if you will? It will hold water if you pour water in. It has a curvature that's curved up, whereas this part of the graph is curved down. It won't hold water, it would fall out. Where it changes curvature from up to down is the inflection point. That is where the derivative reaches a maximum or a minimum. In the next video on this section, we'll take a look at graphing the derivative from the graph of the original function. Join me for the next video on derivatives.